All right, everyone. Welcome to our Chapter 4 section on probability. We're going to go ahead and just dive right in. So, when we talk about probability, the notation we're going to use when we write P of A is essentially the probability of event A occurring. All right, and you can see that right below here. It says what's the probability of event A occurring, and then they're going to define what event A is. And then there's this one, and this is, and sometimes we use shorthand. And if you've never seen that kind of writing, this is less mathematical and more grammatical. It just means copy all those words down below. So the probability of event A not occurring. And finally, what we should say is we should say probability is a real number between 0 and 1. So we don't talk about things being like 70% chance. We would say the probability is 0.70, for instance. And so with those three definitions, let's go ahead and get started. Also, maybe there's one more just to the side, or maybe up top even, is that when we talk about probability, it's maybe this is another way of doing it. Writing P of A is the number of ways A occurs, and this is number of all outcomes. Alright, so in other words, number of outcomes could be another way of saying it, where A occurs, divided by the total number of all outcomes in general. So with those definitions out of the way, the first few questions here are, in my mind, going to be pretty simple and just really get us used to kind of the notation and the verbiage that they're going to use. So go ahead and read this first one. Let A denote the event of placing a $1 bet on a certain lottery and winning. Suppose for this particular lottery there are 7,200 different ways you can select a 4-digit with repetition allowed, and only one will be the winner. So what's the value of A? And A is winning, essentially, right? You want to win, and they just told you there are 7,200 different choices you could make, but only one of them is going to be correct. And so this is where we go to our basic definition, and we would say, well, P of A, the probability that I win is the 1, right? Because there's only one way I can win if I pick the one special number. And how many options or how many different ways could I have picked that number? 7,200. Or how many of those numbers could have been picked? And really, that's it. That's your probability of A. And so if I take that in my calculator, that is going to be, and you might see some new notation in your calculator just to see this. See how that says 1.3888 and then E negative 4. That is shorthand for scientific notation. So the way I would actually write this is 0.000138, etc., etc. And so you can see there what this E to the negative 4 then represents is the fact that it used to be 1.3 on the calculator, but because it's E to the negative 4, they're saying move that decimal place to the left 1, 2, 3, 4 places now. And so there was a 1 in front, so now there's 3 extra leading zeros in front. We're moving that decimal place over, and that should make sense that this is a very small chance that you would get it right. Well, then how do I find the complement? So they want P of the probability of the complement of A not occurring. Now there's two things you can do. Is you can either kind of manually calculate it, or you can have your result and then do the opposite. So one thing to know about the complement probabilities, you can literally just do 1 minus, and I can kind of copy that answer. And so now I get 0.999861 repeating. All right. And of course, your online homework will tell you how much they want that rounded to. The other way of doing that, of course, is if there was 1 out of 7,200 that were correct, then there's 7,199. So it's still the same idea, 1 minus um, divided by still the 7,200. And that's going to be the same decimal. So it's up to you how you want to think about that. Did you already get your correct answer in part A? Then just do 1 minus your answer. Or do you want to think about fractionally what does it mean to have not the one right answer? Well, then you have one of the 7,199 out of the 7,200. But either way, that's your complement probability. All right, up next, what we're going to do is, again, just get accustomed to what does it mean by number of ways that A occurs divided by total number of outcomes. So we have 3 different little scenarios to go through. So find the probability that when a single 6-sided die is rolled, the outcome is 4. Well, how many ways can your outcome be 4 on a 6-sided dice? Only 1. How many outcomes are there in total? Well, 6. And so 1 out of 6 would be 0.16 repeating. Again, look to your homework to see how many places they want. They're probably going to want it to 3 or 4 places. So what you could do is, they're probably, if they wanted 4 places, you would do 0.1667 because you have a bunch of 6s afterwards, and the 6 would round up to 7 in that 4th decimal place. All right. Up next, if you toss a coin that results tails, well, on a coin there's 2 sides, so only one of them is tails, and there's, well, 2 sides. That would just be 0.5. And here's another interesting one. Find that when a 6-sided die is rolled, the outcome is 10. Again, they're kind of playing on your knowledge of a regular dice, and you should know that that's 0 out of 6 because this is one of those impossible events, right? The dice is labeled 1 through 6, so there's no way you're going to get an outcome of 10 by just rolling 1 dice. They're kind of trying to trick you, but they're also trying to introduce the idea early on that there are some probabilities or there are some events that will never occur, and sometimes they sound obvious to us out loud, but sometimes we find mathematically the result is 0 and it's not as obvious, but they just want to show us that early on. As maybe a 4th example, I just feel compelled to add this in, we could also say the probability of, let's see here, rolling a number greater than 4 on a 6-sided dice or die, however you want to say that. Excuse me. So, well, if a number is greater than 4, let's think about that. What are the outcomes that are greater than 4 on a 6-sided dice? Well, there's 5 or 6. That's 2 outcomes. And how many outcomes were there in total? Well, 6 in total. So this time I would end up getting 0.3 repeating. Right? There's a 33% chance, 2 out of 6, that I get a number greater than 4. So just showing you there that that's what we mean when we're calculating the number of ways A occurs, right? Because here, the way A is defined, it's getting something greater than 4. And there's more than one way of getting something greater than 4. It could be 5 or it could be 6 on my 6-sided die. And so I take both of those and put them together and count them, so to speak. And then I divide it by the count of how many options there were. And we're good to go. All right, up next, it says which of the values cannot be probabilities. And remember up top here that we said a probability is a real number between 0 and 1. So let's look at our options. 0.05, that is between 0 and 1. And careful, we're looking for the values that cannot be probabilities. So we're going to circle the ones that can't be probabilities. Well, 0.05, that's essentially 5%. That's fine. What about the square root of 2? You might not know it, but you can type it in. That's actually greater than 1. So square root of 2 cannot be a probability because it occurs more than essentially 100% of the time. 0 is fine because, again, 0 is included. We already saw that right up above. 3/5, that's fine. 1, that's fine. 5/3, careful, 5 over 3 is greater than 1, so that's not allowed. Negative 0.6, that's also not allowed. And 1.27, that's also not allowed. So again, It can't be negative, it can't be greater than 1, and just be careful to follow a calculator to determine if it is greater than 1 or not. All right. Up next, we have assuming that 200 births are randomly selected and 96 of the births are girls. Use subjective judgment to see if this is significantly high, significantly low, or neither. Now, the idea here, and it probably will say it in the little blue text underneath, but 96 out of 200 is 0.48. All right, so let's write that down. 96 divided by 200 equals 0.48. And so I'm going to say this is not significantly low or significantly high. And here's the verbiage I'm going to say out loud but not write out fully. Is I think we would assume that at birth we would probably expect 50% girl, 50% boy at birth. And so in that sense, being 48% versus 50% doesn't seem statistically significant or not. It's not that far percentage-wise. Now, if we saw something like 30% or 20%, that would be, probably significant. So we're using some, again, subjective judgment, as they even say in the wording there. Hey, it should be half and half, but randomness is going to occur. So, again, you might flip a coin, right? That's also half and half. You might flip a coin, and you might not get an even amount of heads and an even amount of tails, and that's because randomness occurs. But what you expect over the long run would be something near 50%, and so we're reasonably near 50% there. All right, up next we have odds in favor, odds against is kind of the quick concept here. Just to show you there are other ways of kind of talking about the parts of the fraction that are a part of our probabilities. So when we say odds in favor or being 39 to 61, what that means is there's 39 favorable outcomes, right, where A occurs, but the total outcomes are the 39 where my event occurs and the 61 where my event doesn't occur. Now, for this example, it ends up being a pretty nice little number, and we get 0.39. But just be aware that when we talk about odds in favor, what we're doing is we're saying, hey, you need to add those two up to get your total number of outcomes. You just know your yeses versus your nos, but probability is all your yeses divided by all your options, the yeses and the nos. So again, just some different phrasing, but it's the ultimately the same probability concept. All right, onwards. In a genetic experiment, one sample had 401 green peas and 24 yellow peas. Based on those results, estimate the probability of getting a pea that's green, and then is that result reasonably close to the 3/4 that was expected? So let's see here. Well, we want the probability of getting a green pea. So sometimes when we say our probabilities, we could write it using letters, right? The probability of getting green. And so that would be, well, the 401 where I would get a green pea. But then it would be 401, kind of like we just did before, plus 24 to get 425 as our final denominator. Now let's see what that is. And that's looking like, I guess I'll write approximately because I'm going to round, 0.9435. And then is that result reasonably close to the value of 3/4 that was expected? I would say no. And I would say it appears to be higher. It appears to be higher. I might even throw the word significantly in there. Because again, if you were expecting 3/4 or essentially 0.75, getting 94% is a lot more, certain or almost close to being guaranteed compared to every 3 out of 4. All right. Up next, we have, let's see here, each of two parents of the genotype blonde red, which consists of the pair of alleles that determine hair color. And each parent contributes one of those alleles. Assume that if the child assume that if the child has at least one blonde allele, that color will dominate and the child's hair will be blonde. And then it says list the different outcomes. So this is, if you haven't done it before, in biology we call these Punnett squares. We're not going to write it out as a Punnett square, but we are going to essentially say, well, from the parents, each one has a blonde and a red, and they're each going to give one of those alleles. And so what are my options? And my options are, it could be from parent 1 I gave blonde, and from parent 2 I gave blonde. Or it could be from parent 1 I gave blonde, and parent 2 I gave red. Or it could be from parent 1. So you can see from parent 1 I've already had the two outcomes where it's blonde or blonde. Well, it could be also that parent 1 gave red and parent 2 gave blonde. And finally, it could be that parent 1 gave red and parent 2 gave red. And those would be our 4 different outcomes. But now, here's the interesting thing. Even though there's 4 different outcomes, remember what it said here is that if the child has at least one blonde allele, it will be dominant and the hair color will be blonde. So what is the probability that a children will have the red genotype? Well, after writing that out, we can figure out that it's 1/4. And so what's the probability that a child will have blonde hair? Well, that would be the opposite, 3/4, right? Because as long as blonde shows up in 1, that will overtake. So there's 1, 2, 3 out of the 4 total options where blonde was present at all, so blonde would dominate. All right. So again, that's just some basic biology. And again, if you've seen the term Punnett square, that might sound a little familiar to you. All right. Up next, we're going to step it up with 4.2, and we're going to deal with what they call the multiplication and addition rules. So, first, we have the probability of, in just some kind of complement review, getting food that is not from restaurant A. Now, you can see that there's a little StatCrunch label here, and one thing that we'll make use of in StatCrunch, and I'll show you how to do that in class or maybe in a separate video, is there is a way of essentially taking this data and having the totals provided. But for now, I don't really have them, but I can go ahead and calculate those totals. I'll need them because probability always involves total number of outcomes on the bottom somehow. So 279 plus 55 is 334. 245 plus 34 is 279. 139 plus 15 is 154. And I'm going to verify the rest here real quick, but I trust you could do that. Alright, so I've gone ahead and made sure I totaled up all those columns correctly, totaled up the rows correctly, and then crossed my totals with my totals, and then added them all up in the middle just to be sure. But again, there is a StatCrunch way of getting your totals for free. But now, when they say, find the probability of getting food that's not from restaurant A, this is where I'm going to use more explicitly the complement formula. So I'm going to do this formula. The probability getting something from not restaurant A, and I know we write like event A, but it kind of works in this case. The probability of getting something not from restaurant A is 1 minus the probability of getting something from A. And now I got to work that out. What is the probability of getting something from restaurant A? Well, there's 365 orders that were from restaurant A divided by the 1,132 total orders. All right, and so if I simply work that out, and make sure you type that in carefully in your calculator, make sure you type in, sorry, you can see all my cross-checking, but make sure you type 1 minus parentheses the 365 from A out of the 1,132 in total. And that's how I'm calculating my probability. If you type this in without parentheses, just to show you, and again, that's incorrect, it will do maybe some funky math. Well, actually, in this case, it's fine because it will do the division before subtraction. It will follow PEMDAS, but still, just be careful. You want to do it in parentheses. In this case, it was fine, though. Anyways, we end up getting, there's a 67, essentially 0.77 chance if we round to 4 places. Sorry, 0.76. I can round to 4 places. 67.76% chance, but as a probability, again, it would be 0.7 or 0.6776. Goodness. Going further, you can see find the probability of getting an order that's not accurate. And although that sounds like a complement probability, the good news is order not accurate is an entire row that I have the total for. So I can just say maybe even probability of NA, right? We can abbreviate that however we want, but hopefully you understand that that's what I'm saying is not accurate would simply be, and this time I actually have that count. It's the 139 over, again, the 1,132. So right now, we're really, although they would call this the addition property, we haven't actually had to do addition, but what I want to do up next is before we continue, I want to show you why we're referring to all this as the addition rules. And it's because, right, theoretically, what you're doing in this example, although we're taking shortcuts and cheats, when we say what's the probability of not getting something from A, we're technically saying what's the probability of getting something from B that's accurate or not accurate, C that's accurate or not accurate, D that's accurate or not accurate, and we're adding these together. And similarly for something from restaurant A, notice we jumped right to the bottom like column total of 635, but technically we're saying, okay, what's getting something from A? Well, I'm either getting an order that's accurate or not accurate, but it's from restaurant A. And so what we learn is when we verbally can break something down to or, that usually means add, and when we can break something down to and or a separate event, that would be multiplying. All right. So what you need to do is you need to hear when we're finding a restaurant order that's not from A, we're saying it's B accurate or B not accurate, C accurate or C not accurate, D accurate or D not accurate. And technically there's ors in between all those, right? It's either from B or C or D, and it was either accurate or not accurate. And so that's a lot of ors, and so we're really adding all those up, right? After all, if you work out the fraction math here, what you get is all three of these column totals added together is what this ends up being, as your numerator if you actually worked this out before going right to the decimal. So just be aware of that. Again, getting an order that's not accurate is getting a order that's not accurate, or a B order that's not accurate, or a C order that's not accurate, or a D order that's not accurate. But right here at the end is a total, which is the addition of A or B or C or D, all put together in the non-accurate category. And so we can just take that one number, but we have that one number because we were technically adding stuff in the table all along the way. We just put it on the margins ahead of time for you. But that's, again, why we call it the addition rule. If you can phrase it in a way that says, what does it mean to be not accurate? Again, not accurate means the 35 from A, or the 55 from B, or the 34 from C, or the 15 from D. That is where we're getting the or in the addition in this column total, right? Because a total comes from addition, we would say verbally. All right, now let's step it up and see what happens now. Find the probability of getting an order from restaurant C or that an order is not accurate. Now this is where we're actually going to drill down and get a specific formula. And the formula will look like this. The probability of A or B, this is a mathematical way of writing or, is equal to the probability of A plus the probability of B minus the probability of A and B. And I've run out of space, but that says the probability of A plus the probability of B minus A and B. Now what's interesting about that early on is you can see that or and are on opposite sides here. Again, that says A, and instead of being a U like a cup, it's a kind of N like a and. So A and B, that's what that says. Now let's see what that does for us here and see if we can dissect this formula and also show you the practical way of doing it when you have one of these what we call two-way tables. So getting an order from C or an order that's not accurate. Let's look at what that is. So I'm going to write it like this. Restaurant order from C or is not correct. I'm just going to write it like that. Would be this. Probability of getting an order from C plus the probability of getting an order that's not correct minus the probability of getting something from C that's also not correct. And we'll talk about why we're subtracting that, but it is going to be important. So let's work this out one at a time. Getting an order from restaurant C would be my column total of 279 over the 1132. Getting an order that's not accurate, we've already done that, is the 139 over the 1132, and that's kind of nice. We have common denominators. Now getting an order from C that's also not accurate, finally we're going into the middle of the table, and that's just that 34 right there. Still over the 1132. Now what's convenient, and what's going to become like a cheat for us later on, is the fact that you could take all those, since they're all over the same denominator, because they're all probabilities that are over the same total number of outcomes, you can actually add and subtract just your numerators together, right? Because your denominator already is common. And I get 384 over 1132, which is approximately 0.3392 as a probability. So, essentially about 34%, if you want to say it that way. Now, what's the other way we can calculate this? Great question. And also, why do we need to subtract this 34 here? Great question. Let's look at what it means to be from restaurant C and not be accurate. Now, see what I did here, C, maybe pun intended, is that I took the column or row totals and then this one section from the middle of the table, and let's think about that. What does it mean to be from restaurant C? Well, that 279 is this 245 in the middle of my table and the 34, so I'm counting both of them. So to be from restaurant C, I could either be accurate or not be accurate, and so I'm putting them together and adding them. And then, or I could not be accurate. Well, I could not be accurate 35 from A, or not be accurate 35 from B, or not be accurate 35 from C, or not be accurate 15 from D. But wait a minute, as I count up these 4 for not accurate, and I count up these 2 from C, I have double counted this 34. It's come up twice. That is why it's being subtracted if you write it out. Now the other way, and I'll just do this on the calculator, is to sit there and say, well, wait a minute, if I just take my, kind of not accurate first, if I take my 35 and my 55 and my 34 and my 15 and I kind of cross those out in my head and say those have already been accounted for, and then I say, well, what's left for restaurant C orders? And I say, oh, well, there's also that 245. Look what I get when I add them up. I still get 384, which was the same as the row total, column total, minus the overlap. I still get, if I just count up each individual things and don't double count that 34 and take the other 245 that I missed, so to speak, because I hadn't considered just C in general as a restaurant I could order from. Again, stop that, slow it down, play it back. Again, you can either choose to take your total and minus the overlap because you double counted, or you can take each part, and remember that you already took this part, so there's only 245 left needed to capture all of restaurant C orders. That's the two ways you could think about these problems. But notice again, it still comes down to adding up common elements or your criteria, because it could be this or this or this or this as you break it down in the table. All right, now we get to multiplication. Now multiplication is essentially when we're dealing with multiple events that either might impact one another or not. And it says, if 2 orders are selected, find the probability that they're both from restaurant D. Now, the way you would think about this is, maybe you're doing like a raffle or something, right? I know it says like drive-through restaurant A, B, C, and D, but you could maybe think about this as being like, The Monopoly rewards program thing at McDonald's. I don't know. Maybe you watched the HBO documentary where we found out that was a scam. Anywho, don't think about these as different restaurants necessarily. Think about them as different locations of the same restaurant. So if I'm McDonald's and I'm wanting to do some statistics on my 4 restaurants, right? It's not competitors. There's the location on 200, the location on 40, the location on so on and so forth. If you're in Ocala, you know what I mean when I say all that. Anyways, let's see the idea here. If I'm reviewing my ticket orders and I want the chances that if I just grab 2 ticket orders out of my database of my 4 restaurants I'm tracking as the regional director or whatever you want to call it, what are the chances that I get 2 tickets from restaurant D, but I could replace them and pick them possibly more than once? Well, this is, first I have 154 divided by the 1132. 154 divided by the 1132. That's my first probability of getting something from restaurant D. Now, if I then take that ticket and put it back into like the big hat, like maybe there's a raffle that we're going to give away some special prize with the receipt code, blah, blah, blah. I think you kind of get the concept, but like, let's say I put that back into the drawing, right? I can win more than once. So then if I put it back, well, then my odds are still the same, 154 over 1132. Right? I picked maybe a ticket from restaurant D, and then I put that ticket back, and I want the chance of getting something from restaurant D again. Well, because I put the ticket back, there's still 1,132 in total, and there's still 154 from restaurant D because I put the ticket back. And so I just take that probability and multiply it by itself, however you want to write that, or you can just literally write it as them multiplying together. But you should end up with essentially approximately about nearly 2%. Right? Or in other words, almost literally 1.85%. Now, this would be considered independent, and the reason is that probability didn't change from event to event. And more specifically, I guess maybe what I would drill down on is my denominator stayed the same. It was always out of the same total. That's usually how you can pick out independent versus dependent events. And also, these could have been dependent because I'm pulling from the same hat, so to speak, right? If I took all these receipt tickets into a hat and pulled them out, it's still the same hat. It's the same type of event. Just to say, if this were to be different and it was find the odds of rolling an even number on a dice and drawing an ace in a deck of cards, those would be independent regardless, right? Because whatever happens with your dice roll doesn't impact the cards in the deck. But when I'm taking receipts out of the same database, so to speak, and then possibly pulling those out again, there is the potential for dependence, but we made them with replacement. Okay, now to counteract that, after that explanation, let's see what happens if you make it without replacement. Whoops, sorry. Well, the first time you choose something, right, when we do part B, we're resetting the problem. We're assuming we haven't picked anything yet. So initially, on part B, we still have all 154 receipts, so to speak, from restaurant D. We still have all 1,132 receipts in total. And I just made one selection, and I know it was from restaurant D. And now it says, make it without replacements. Now what that means is now if I were to pick another receipt from restaurant D, there would only be 153 left because one was chosen. There would also only be 1,131 left because one was chosen, right? So I chose one from restaurant D, so not only did my numerator decrease because those were my D options, but also my denominator decreases because there's one less receipt in total in general. Now, whatever that is, 154 divided by 1132 times 153 divided by 1131, we end up getting 0.0184, and this would be dependent, and not necessarily because the probability changed as my final answer, but because my denominator and numerator was changing for the same named event, right? Because I did this more than once and didn't put it back, the probability of getting D the next time has shifted in 2 places, my numerator and denominator. But really, if it shifts anywhere, that's enough. So by simply not replacing a receipt from the bucket, so to speak, you are changing your next probability, even if you're looking for the same event. Even if you still want a second receipt from restaurant D, you've changed the option space, so to speak, so you can't have the same probability. So you've just created what we call dependence. And hot dependence for choosing from restaurant D. The puns are everywhere. All right, here we go. Up next, this question, I'm going to give you a second to read through, and it's a little bit tricky, but I really want you to try to, as best you can, construct a table out of this. I'm going to pause the video myself because I got some other things to do, but you pause it yourself, try to make this table, and then we'll go through it together and, of course, finish the rest of Chapter 4. All right, so no time passed for you, but hopefully you tried it. So here we go. The idea here is that we need to create a table, just like we've seen before, but we're going to need to be careful about how we name this table. You know what? Let me see if I can move that. Maybe that has less of a kind of reflection of the other page. Anyways, let's see here. We have tests for marijuana use. We have positive results, false results, false negatives, and false positives. So we'll have used and did not use. We'll have positive and we'll have negative. And so that's the idea going on here, is what it means to be a false positive, false negative, things like that, is whether you actually use the drug or not and still get the positive or false results. So first thing I have here is among 141 subjects with positive results, and the trick there is, you can even see I started doing it, 141 doesn't go in the middle of the table. It is a column total, or row total, depending on how you made your table. From there are 23 false positive results. So false positive, think about what that might mean. It means there is a positive result, but it's false. So what does that mean? It means 23 goes right here. There are 23 people who did not use, but got a positive result, and that is a false positive. So there we go. I've just filled out the table. And then from there it says among 151 negative results, kind of interesting, there are 2 false negatives. And a false negative would be, well, I got negative, but I shouldn't have, which means I actually used marijuana, or the person used marijuana in this study. Now from there we can kind of play like a little, I don't want to say Sudoku, but kind of a little math game. And we could say, well, if I have the 141 and 151 along the bottom, I now know there are 292 people in total involved with this study. Similarly, we can play some subtraction games. If there's 141 positive results and 23 of them didn't use, then 118 must have used, and they're true positives. Similar kind of addition games. If there's 151 negative results, but 2 of them actually used, then 149 did not use and they got negative, and that should have happened. Now from there, I get my row totals. I get 120, and I get whatever 23 plus 149 is, which looks like 172. And look, 120 and 172 still add to 292, so I'm good to go. Alright, so we're moving right along. So how many subjects were included in the study? Well, 292. Right? Before I even fill out any questions, I'm just going to fill out the whole table. How many subjects did not use marijuana? 171. I now know that. 172 did not use. And what's the probability that a randomly selected subject did not use? Well, that would actually be your 172 over your 292. So we're good there. All right, not too bad. Up next, we dive into 4.3, and 4.3 has 2 big concepts. Conditional probability, that's the second part, but really quickly, we stop by and visit at least 1. Now, the probability of at least 1, and I'm just going to write it like this. Similar to complement, is equal to 1 minus the probability of none. Or at least, or 1 minus the probability that nobody or nothing had the result you wanted. And so real quick, as an example, if a couple has 6 children, at least one is a girl, and then they're assuming probability of boy and girl is equally likely. Well, the probability of at least one girl is the probability of 1 minus, we'll write it like this, no girl. Now, that's out of 6 children. Now, let's think about what that means. We need to always be able to take kind of a probabilistic statement and move it through what we would call its like logical next steps. So, if I have 6 children and none are girls, then that's 1 minus the probability of, I guess you could say 6 boys. If there are no girls, then there are 6 boys, according to this question prompt. And so, we end up with is 1 minus the probability of a boy times the probability of a boy times the probability of a boy 6 times over. I'm going to write ... because guess what? That's 1 minus the probability of a boy to the 6th power. If you're multiplying that same probability 6 times over, then you just have 1 minus, well, the probability of boy, they assume it's equally likely, is 0.5. In this case, again, it didn't quite matter, but that's okay, to the 6th power. And so carefully type that in your calculator. The order will matter this time because of PEMDAS and stuff. 1 minus 0.5 to the 6th power. Actually, maybe it won't because we do exponents in parentheses before. But anyways, you end up with essentially 98.43. So, if you dissect that, and, 4 if you round to 4 places. If you dissect that and think about it, what that's saying is, if there are 6 children, the probability of getting at least one girl is about 98%. And if you think about it for a little bit, it kind of makes sense, but math is kind of funny that way. But you would think, right, if your first child was a boy, you would think, maybe the next one will be a girl, 50-50. And it's not, it's another boy. And then by the third child, you go, well, I have 2 boys. I'm probably going to have a girl now, right? And you still don't, right? The more it happens, the more it should be 50-50, right? If we say it that way. The more it should be 50-50, and the less it occurs, the more by the next time and the next time, we should at least have one of them being a girl. So that's kind of where this number's coming from, if you could think about it in that way. But again, it's also saying... and we haven't quite gone into this and we don't have time to draw it out, but we'll look at some coin examples in class. But if you really think about what it means to to have at least one girl, it could be the complete total opposite, that you could have 1 girl and 5 boys. You could have 2 girls and 4 boys, 3 girls and 3 boys, 4 girls and 2 boys, 5 girls and 1 boy, or all girls, right? There's all those different scenarios that we could count out. And we're just looking for the opposite of the one scenario where it was 6 boys across the board. So it's actually, again, pretty likely that you would expect to end up in at least one of the scenarios where there's at least 1 girl. And again, we'll find out that even so, just saying 1 girl out of 6 boys has more than one outcome, because it could be the first is a girl, the second's a girl, the third, the fourth, the fifth, or the 6th is a girl, and that's still 1 out of 6, but there's 6 different ways that occurs. We'll expand more on that. All right, but more so what we need to focus on is conditional probability. So, conditional probability, and we're going to write it like this on the side. We'll total these up. Why not? 154, just because we're right here. 154, that's 146, and that looks like that would be 300. This would be 134, and this would be 166. That would also add up to 300. So there we go. We just totaled up our table pretty quick. Conditional probability, though, looks like this. We write it as A given B. It's that vertical line. And that is always the probability of A and B, both of them occurring, divided by the probability of B occurring. All right. Now, the other way you can phrase that is if B's already occurred, what's the probability of A occurring also? There's many different ways of phrasing this, but that's what conditional probability boils down to. Now, if we work on this definition, this is actually going to be pretty easy. What this usually boils down to is simply the number of A and B divided by the number of B. Because we don't actually need the probability over 300 for each of them. And maybe we'll talk about that mathematically real quick. But really, just focus on the phrasing and let's see what happens here. So, the probability of getting someone who tested positive given he or she had the disease. So first let's write that out mathematically. They tested positive given they had the disease. Or maybe even we use the Y and N as they wrote. So the probability of being positive given that I had the disease. Let's write this down now. That would be the probability of positive and having the disease divided by the probability of having the disease. Now, let's work that out traditionally, and then we'll skip and cut down to what I wrote here on the bottom. The probability of being positive and having the disease would be the 140 out of the total 300, because that's what a probability is. It's your outcome divided by everyone. So this is the probability of P and Y, so to speak. Positive and yes, there's 140 out of 300 total, all outcomes. On the bottom, what's the probability of yes? The probability of yes is 166 out of 300. Now, before I work this out, let's be a little bit mathematical, and remember that if you're dividing fractions, here's another way of writing this. This might jog your memory. You end up doing keep, change, and flip. And watch what happens now. Your 300s cross cancel because they're on the top and the bottom. And you end up with 140 over 166. And that's where I get this formula down here. It's the count of your ands, the count of yes and positive, 140, divided by your count of, in this case, yes. And my count of yes is 166. So 140 out of 166 ends up being 0.8434 to 4 decimal places. Again, it's whatever your homework deems is necessary for probability. Alright, using that shortcut on the next example, find the probability of getting a subject with a negative result given they had the disease. So let's write that out. Negative given they had the disease. Well, I'm looking for my negatives who have the disease, which is 26, divided by the yeses in total, which is 166. And, well, 26 out of 166 is 0.1566, so about 15% of the time. And then it says what would be an unfavorable consequence, so let's sit and think about that. If we had the disease and they got a negative result, the consequence would be that 15% of the time we're telling someone they don't have a disease when they actually do. So 16 or almost 16% of the time we're not giving people maybe treatment that they need because we misdiagnose them as being okay. That would be the, as we call it, unfavorable consequence. And last but not least, we end up with combinations, permutations, and counting. This is, I like this section a lot, but you might not like it. But first, let's do some vocab or some kind of notes up at the very top, really short in the margins. We'll learn about factorial. If you've never seen factorial, if I write 5 factorial, you should know that that's 5 times 1 less, which would be 4, times 1 less, which is 3, times 1 less, which is 2, times 1 less, which is 1. And if I multiply all of those together, let's see here, I get 5 times 4 times 3 times 2. I end up with 120, because the times 1 actually doesn't matter in this case, but that's what a factorial means, and we're going to see those a lot here as we get into the combination section. Now again, your calculator will do combinations and permutations for you, but it's still a good idea to know what they are up front before we dive in. So, if I write NPR, now what that means is if I have n total choices and I want the permutations of choosing R of them, what I end up with is n. 1 minute. Oh, I gotta think about it. Yeah, it would be n factorial over n minus r parentheses factorial. And don't worry, we'll work some of this out. And then for combinations, NCR, and you'll see these buttons on your calculator, and we'll talk about them. It's n factorial over still n minus r factorial, but we multiply an additional r factorial on the bottom for mathematical reasons we don't have time to entirely discuss. But the main thing is, what you should be aware of is, hey, if we're dividing something extra for NCR, there should always be less combinations than permutations. And the last thing to say there is, and we'll just write it under here really shortly, order doesn't matter. And then here we'll say order matters. Really, really quick shorthand, but usually a lot of us learn that is that permutation is where order matters, combinations is where order doesn't matter. Now, even so, we might not be fully into that section yet, because we also just have general counting. And counting, just to say out loud, is where you multiply every last choices option by every next choices option, and together you get your sample space, or how many options there are. So here we go. It says a thief steals an ATM card and must randomly guess the correct 3-digit PIN from a 6-digit keypad. Now again, this isn't real life, because usually keypads are 10 digits. We have 1 through 9 and also 0, but anywho, it's just a scenario to get us a little bit into the space of answering these questions. But it says, what's the probability of getting a randomly correct guess on the first try? And well, here's the idea, is that if I have a 6-digit keypad and I have to guess a 3-digit code with repetition allowed, then my first choice has 6 options. I could choose any one of the 6 keys. My next choice still has 6 options, because even though I might have already clicked the 1 or the 2 or the whatever digit, I can repeat those digits. And then my next one, I could still choose another one of those 6, and if I multiply those all together, 6 cubed ends up being 216 total different codes I could make from a 6-digit keypad, choosing 3 of those digits. And so what's the probability of getting it right? Well, 1 out of 216, and that's it. Alright, so we're listing the sample space, and then we're simply taking 1 over that, because that's my one correct answer, so to speak. Alright, up next, social security numbers have 9 digits, and repetition is allowed. And then suppose someone saw your last 4 digits on a receipt or your tax return or whatever. If you could randomly guess the other 5, then now you know that correct full number, right? So after seeing the last 4 digits, you have to randomly select the other digits. Well, there are, again, 10 digits, because you could have 0 and 1 through 9. So that's literally going to be 10 times 10 times 10 times 10 times 10. Repetition is allowed. That's 10 to the 5th. And so then the probability would be 1 over 10 to the 5th. And let's maybe write that and see what we get. So what is 10 to the 5th? It's 10, well, with 5 zeros at the end. 1 divided by that number is, well, we get E and then negative 5. So again, that means we had a 1 up front, and we moved the decimal 5 places, which means we end up with 4 leading zeros, and then the one that used to be up front in general, right? It used to be here, and then back 1, 2, 3, 4, 5. That would be my probability. It's still, theoretically almost impossible, or in other words, you have 100,000 wrong guesses. And I bet whatever online banking system or whatever, if you get even at least 10 wrong guesses, they're going to stop you there. So hopefully you get lucky if you're being a thief, or hopefully you don't get lucky if you're just a regular person who doesn't want their identity stolen. All right. Up next, here we're going to move into different phrasing, and we're going to move into possibly combinations or permutations. Let's find out. In a horse race, a bet is won if you select the 3 horses that finished first, second, third, and they can be selected in any order. Interesting. And there are 20 horses. Find the probability that you get the correct 3 horses. Now, again, we said permutation order matters. In combinations, order doesn't matter. Now, the weird part about that is it says first through third, right? They're naming them in their positions, but then it says afterwards it can be selected in any order. Now, you might not know where this button exists on your calculator, but this would be an example of doing 20. And then I'm going to hit my stat key and do, maybe not stat. Where is it? I've got the button here somewhere. We're going to find it. Math, probability, and CR. And whoops, that would be 20, C3. And there would be 1,120 ways to correctly guess the 3 horses. 1,140 different 3-horse combinations that would get you into the winning bet. And, of course, the right bet would be the one that actually occurs out of the 1,140 that were possible. So notice that, again, it took me a little bit of searching and finding it in my calculator. For me, I had to type the 21st. Then I have to press the math button and go to probability. I've got a little bit of a fancier calculator, but there is a way of finding either combinations or permutations and then getting your result. And I'm more than happy to look through that with your calculator and make sure you know how to get there for yourself. All right, up next, it says that in a rugby match, a tie at the end of 2 overtimes leads to a shootout with 5 kicks taken by each team from the center, and each kick must be taken by a different player. And we just want to know how many ways can 5 players be selected from the eligible 15. Now, that is another, and this is why it's nice to have a calculator that can go back. This is another combination question, because if you read this, it's just saying out of the total 15, choose the 5 that you want in any order. And there's 3,003 ways we could select 5 players out of 15. And honestly, I mean, it's kind of just a stop-pause moment, because those numbers sound pretty insane, right? In our class or in any one of your classes, think about the 15 people in a room, and if someone said, hey, pick 5 people and go, do a group together, I bet you wouldn't necessarily think there's 3,003 ways just for you to group up with 4 other people in a class of 15. But there are. And then, here's the crazier part. What if instead of just saying, who are my 5 that are going to kick, it's now, who are my 5 that are going to kick, and what order do I want them in, right? And look at that. We have an enormous amount of options of not only saying, here are my 5 people, but then what order will those 5 people be in? And that gets kind of astronomical. Now, this might be the correct answer, but I'm pretty sure this is what they're going off of. This is how many ways can you choose 5 people in a particular order. I would assume that's what they're asking. But also, just saying, the other way of saying that is, once you've chosen your 5, we could phrase it this way. We'll see which one of your homework wants, or you'll figure that out. But once you have your 5 players, how many ways can you order your 5? That might be also what they're asking, which would be 120. And I think if we take 120 times our 3,003, Whoops. Yeah, that's where that number's coming from. So, just showing you that it could be either of those two. Based on the wording, for the 5 selected players, how many ways can we order them? I think it's going to be the 120 as your answer. But just so you know, in general, if you take it from the top to bottom, there are technically almost a third of a million, more than a third of a million ways to just choose 5 players and order them. Interesting. All right. Up next, speaking of orderings, we get some interesting questions here. Like, how many ways can we order the word eggs and rearrange it? Now, I should have gotten a colored pencil or pen. Give me a second. Also, I keep realizing I say give me a second, and then I realize that I can pause the video, so it's fine either way. Well, let's actually write them all out. So, it could be, and here's how I'm going to write it. It could be G E S. It could be G E S. It could be, thinking ahead here, GGSE, and then GGSE. Now what I want to point out early on here is that what hopefully you can notice is that I chose some different colors to write my G's in because they're the same letter, but ultimately that order won't matter. And so essentially, if you think about just essentially saying, and here's what we're kind of saying, how many ways can you have 4 items and permute them, right? Totally order them in any way. I would get 24. But I'm going to go ahead and tell you that the answer here is not 24. It's going to end up being most likely less because out of these options, really, so far I've only listed 2, even though I wrote down 4. And so maybe you're seeing where we're going. Maybe the E goes first, and then maybe the ES goes, and then maybe the SE goes. But really, there's only 2 options here, and so we're double counting in some way, and the question is, how am I double counting? Now, here's how we solve questions like this. And the problem is there's repetition of letters. So I'm going to write it down like this. It's n factorial, which is your number of letters, divided by a 1 factorial, a 2 factorial, blah, blah, blah. And I'm going to write a k factorial. Now, A, when we write A sub 1, A sub 2, A sub 3, we'll say where AI is the count of the repeated ith letter. Alright, so how many ways can we rearrange eggs? Well, here we go. There are 4 letters, so 4 factorial, which would be 24. But here's the issue. The G is repeated twice, so AI, in this case, is not artificial intelligence. It's saying the letter that I first see repeated is G, and the amount of times I see it repeated is twice. The count of the repeated ith letter. So that's all I have is there's 1 letter that's repeated twice. So there's a single 2 factorial on the bottom. And well, again, factorial, just to review, would be this. 2 factorial will be this. The 1s cancel, and also 1 multiplying doesn't really matter. And the 2s cancel, and that's fine. And so I end up with 4 times 3, which is 12. And so maybe now we can write out those 12, right? We could have the GGES. We could have the GGSE. We could have the GEGS. We could have the GSGE. And you can kind of see what we're doing is we're passing along the G's. At first they were both on the left. Now there's 1 on the left, 1 in the middle. We could then put maybe the GESG and the GSEG, put them on the ends. And then from there we just keep on cycling through. So maybe we start moving that other G closer. So we then say it could be EGSG. It could be SGEG. I feel like I'm missing something here, but we'll get there. Nope, never mind. We're fine. Then it could be the EGGS, the actual word that we started out with. That is one of the possible values. So the 2 G's in the middle. And finally, it could be the ESGG or the SEGG with the G's on the end. And there are my 12 options. And notice that, again, the G's, although they're written right next to each other, right, they should be colored separately. But then afterwards we realize, oh, I didn't actually need to care about the other ways these G's could be oriented. It's the E and the F that's going to make the difference in the words, is the idea there. Right, so here, right here, we counted those 2 possibilities right up front, and we saw that we had double the amount by caring about the order of the G's. So we had to undo, or essentially uncount, the 2 different ways we could arrange those repeated G's. Alright, well, based on that then, let's see what we have now. Balloon has 1, 2, 3, 4, 5, 6, 7 letters. So we've done the heavy lifting now. Let's just do the math. We have 7 letters. And on the bottom there are 2 repeated L's. There's 2 repeated O's. And so I end up with, let's write it out because it'll be kind of fun to watch it cancel out. Now, it's up to you. You want to think about it. I think for me, what I'm going to do, as a lazy mathematician, I'm going to say, well, these 2's can cross cancel with the single 4, right? 2 times 2 is the same as 4. So what I have now is 7 times 6 times 5 times 3 times 2, because essentially that got rid of the 4 in the middle, and I got 1,260 different options. All right. Finally, there's the word statistics. Now there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. 10 letters. Let me make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. But I'm seeing that there are 2 I's. There are 3 S's. And there's also 3 T's. I'm pretty sure I got all my repetitions right. Again, 1, 2, 3 T's, 1, 2, 3 S's, 2 I's, and then there's an A and a C, and that's about it. Right? Because 2 plus 3 plus 3 is 8, and then, yeah, the A and the C make 9 and 10. Great, we did it. So again, it does get a little complex sometimes. Be careful that you're counting correctly, but here we go. That's 10 times 9 times 8 times 7 times 6 times 5. Now you can do this all in your calculator, but I still like doing it by hand. Eventually you don't have to write the times 1 because we know what that's going to be. We've got 2 times 3 times 2 times 3 times 2. Now those 3's will cancel out the 9. And if you also think a little bit ahead, those 3 2's will actually multiply to 8. So we just canceled that out. So we have 10 times 7 times 6 times 5 times 4 times 3 times 2. Or, again, you should end up with 50,400 different ways. Right? And these are pretty small words if you think about it, but it would be a big pain to write out all those different possible combinations, but we at least know how many there are without needing to actually write them out ourselves. Alright, we're almost done. We have just a few different questions now, still dealing with kind of combinations, permutations, and counting, so here we go. It says the winning jackpot in a particular lottery, we have to select 4 numbers between 1 and 52, and then there will be another single number between 1 and 25. So, like, if you've ever watched the lottery, or if you've ever played the lottery, you don't actually need to get your number choices in order. You just need to choose the correct ones. So, this is going to be 52 choose 4. And then we're going to multiply that by, well, I guess, 25 choose 1. Which is actually just going to be 25. Because, right, there's only one way to get one number out of 25. You got to pick the one out of 25. But even so, we can use our calculator, and I can write it in parentheses. I can say, okay, I've got my 52, and I want to choose 4 of them, and put that all in parentheses, and multiply that by, I've got my 25 for my extra special number, and I just want to choose one of them. Again, you'll still see that that's 25, and in this case, when you multiply that, we get, I don't know why I put the 2 first. We end up with 676, 8, 1, 2, 5 different options. And so that's your different options, and so your probability is, of course, 1 over that very large number, so that would be a very small chance of winning. In other words, you should not be playing the lottery because there's more than 52 numbers, and you also make more than 4 choices, so your odds end up being astronomically even less. All right, up next, this is the big last final question. It kind of covers everything. It still is related to what we've done, but let's see what's going on here. So we have 2 companies that are merging, and company A has 7 executives, and company B has 5 executives. And there will be a new executive team of 6 members, with 3 of them coming from A and 3 coming from B. And the team will have 3 roles. There's essentially operations officers, essentially co-COOs, co-CFOs, and co-CEOs, if you've ever heard those terms before. So we need to essentially, right, choose 3 positions from A to be COO, CEO, CFO, and 3 positions to be COO, CFO, CEO, from B. And then we need to think, how many different ways could those be put together? Now, it's not too bad, but what this honestly comes down to, and it's pretty simple once you see it, is it's 7 permutation 3. Because from company A with 7 executives, 3 of them will be chosen to be essentially, again, an operations officer, a finance officer, an executive officer. And the reason this is a permutation and not just a combination is because we're not only choosing 3, but we're then assigning those 3 distinct roles after the fact. And we're simply going to multiply that by the amount of ways we could choose it from company B. Now, company B has 6 members, so it's 6 permute 3, but we're still choosing, again, 3 from A and 3 from B. A new OO, FO, and EO, a new OO, FO, and EO from A and B, so choosing 3, but they each can have different roles. How many different ways can we slice those up and have people working together? You'll be surprised, even though those numbers are relatively quote-unquote small. If I have 7 permute 3 times 6 permute 3, and I just don't quite like how that looks, so let me get my parentheses there just to make sure it looks nice. There we go. And there's 25,200 different ways that could occur. So, right, even with just a small amount, right, we think like, 7 people and 3 people, let's just assign some roles and move on. Really, there's a ton of different options, which is kind of surprising to think about. And with that, you've now survived Chapter 4. It's a little bit of a different section. It's kind of a mind-melting section. Make sure you read the problems carefully, practice, think of combinations, permutations. Is it or, is it and, is it conditional? There's lots of different phrasings and verbiages and formulas that are going to show up. Follow them carefully, and good luck, and I'll see you for the next section.